Okay, good morning, everyone. So my name is Brian Goetz. I'm the Java language architect at Oracle. And for the last 4 years, I've been working on bringing Lambda expressions to Java. And that's finally done. It's shipped. And I can think about other things, which is wonderful. And I can stop answering the question, when can we have it? Because the answer is already. So just a couple quick questions to see who's in the audience here. How many people are here today? Okay, good. All right, you passed the first question. How many people here would consider themselves Java programmers or programmers of some language on the JVM, like Scala? Okay, good. You're all in the right room. Okay, this one is harder. How many people here would say that they're familiar with the Java bytecode instruction set? A couple. How many people here have used the Java P tool to look at the bytecode of some Java class you've written? Okay, so about a third to half of you have actually seen what bytecode looks like. So that's a good start. I'm going to be diving into the depths in this talk. If those of you who didn't raise your hands, either of the last two questions, are curious and you've got a laptop, write a trivial Java program, compile it, run Java P-C to see what the, and we'll decompile the bytecodes for you, and you'll get a picture of what the Java bytecode instruction set looks like. It's an architecture-neutral instruction set. It's stack-based to abstract away from things like register allocation, and of course, the JVM consumes bytecode, and then at runtime turns it into native code. The reason I bring up bytecode is this talk is not just about what are the new language features in Java 8. In fact, it's hardly about that at all. It's more about how did we make the key decisions that we did make about what Lambda in Java should be. Everyone had an idea of what Lambdas were. Java was what it was, but there was a great deal of design space to be covered about what do Lambdas mean in the context of Java. And there were some hard questions to answer there and some surprising answers, and I'll talk about those. And I'm also going to talk about the details, the low-level details of what bytecode is the Java compiler supposed to emit when it comes across a Lambda expression, and what is the VM supposed to do with that? And the reason we care about that so much is it's not simply a matter of providing the right programming model, right? So developers work with code all day. They see the source code in front of them. That's how they think, and that's great. You want to give developers the right abstractions to program with and all of that. But if the constructs that your programming language gives you are not a good match for how the underlying environment is going to execute those instructions, you're going to have a mismatch, and that's going to cause pain points, it's going to cause performance anomalies, and we don't want that either. So the design process of add Lambda to Java, which sounds like such a simple question, is one that goes much deeper and has to go all the way down to the metal in order to have what we consider to be a good implementation. All right? So I'm going to talk mostly about what's below the level of the language. Okay, so this is how you know I work at Oracle. I have to put up this slide. Blah, blah, blah. Don't make any purchasing decisions based on what I'm going to tell you. Blah, blah, blah. Okay. So this is going to be a technical talk. I'm going to show you bytecode. If you're not familiar with bytecode, you should fake it and say, yeah, I can imagine what that would do. I'm going to talk a little bit about some of the features that were added to the JVM in Java 7, invokedynamic and MethodHandles, which are very cool. And most people don't know about them because these are low-level tools designed for compiler writers. So if you're a compiler writer, these are wonderful tools for being able to allow people to express things that have more dynamism in them and still be able to implement them very efficiently on the JVM. So I'm going to go through some of the JSR 292 tools that we use in order to achieve this with Lambda. Okay, so a couple slides of background, and then we're going to jump into the technical details. So in case anybody doesn't know what a Lambda expression is an anonymous method. Has everything a method has. It has an argument list. The arguments have types. It has a return type. It has a body. It has a set of thrown exceptions. It just doesn't have a name. And the syntax for Lambda expressions in Java is very much like the syntax for Lambda expressions in C# or in Scala, except that we use the thin arrow instead of the fat arrow, and there were reams of discussion about why that was, and we're not going to get into that. So in the top example, you have a simple example of a method that's designed to take a Lambda expression. And this particular method is a for each method on collection, so it takes as input an element, in this case a person, and the body is invoke the getName method on the argument, and then add that to some collection. One of the things that we did to make life easier for people is we added a great deal of type inference to the Java compiler. This doesn't make Java dynamically typed in any way. It's still purely statically typed. It's just that the compiler got smarter about not making you repeat yourself with type names all the time. So the second example shows how you can omit the manifest types on the argument list, and if you've used generics properly, which of course we all do, right? How many people here use generics properly all the time? See, all of you. Okay, no problem. So this actually is one of the, I don't know if it's fortunate or unfortunate side consequences of adding Lambda to Java. We lean much more heavily on generics, which means that if you suck at generics, you're going to get error messages from the compiler that you can't read. And this is our way of motivating you to get better at generics. Does that seem like a good plan to everyone? Okay, good. So in the second example, we show an example of better type inference where the compiler looks at the signature of the for each method. It says people is a collection of person. The for each method takes a consumer of person. This Lambda expression has one argument, therefore it must be person. So I'll assume that. I'll type check it, make sure everything's consistent, and everything's good. You know, we move along. And finally, I want to highlight the fact that Lambda expressions can capture values from the enclosing context. So there's an example at the bottom where you say, take the collection of people and remove all the ones whose age is less than some minimum age. Minimum age isn't defined inside the Lambda expression, so it must be taken from the lexical context outside the Lambda expression. Names in Lambda expressions that aren't parameters basically mean the same thing inside the Lambda as outside the Lambda. So they're in that way, they're much simpler than inner class instances. And that's kind of all you need to know about Lambdas in Java for the purpose of this talk. Obviously, there are many other talks that can be done about all the cool things you can do with it, and that's a talk for another day. Okay, so a little bit more background about why we did this, because believe it or not, people ask. So there's a lot of reasons why we finally decided to add Lambda expressions to Java. The big ticket one was we need a better way to enable people to write code that runs well on multi-core systems. So the way that we do everything in Java is with libraries. Well-written libraries are leverage for programmers. You can reuse the work of others. So we want to have parallel-friendly libraries. In order to write good parallel-friendly libraries, you need a mechanism for internal iteration. In other words, be able to say, here's a unit of work, do this for every data item in your collection, and let me know when you're done. And so in order to efficiently express internal iteration, you need a way of passing little snippets of behavior around, and that's what Lambda expressions do. So that's really the high-order motivation for it. Of course, there's hundreds of other reasons why Lambda expressions just make you a better programmer. We want to empower libraries to deliver more effective libraries, libraries that enable a greater degree of cooperation and permeability between, in the boundary between the client and the library. And finally, it's just kind of about time, right? I mean, Java's the last holdout among mainstream object-oriented languages to not have closures. And 5-10 years ago, it might have been a radical idea to say Java should have closures, and it's no longer a radical idea. So the counterpoint to that argument is, well, why did you bother? Java already had inner classes, and inner classes are great, right? Everybody loves inner classes. Well, so inner classes were an attempt in 1997 to add some of the benefits of closures to the language. It was an okay attempt. But ultimately, they were too clunky to get the job done. And the clunkiness, I think it's important to note, is not entirely syntactic. A lot of people look at inner classes and say, the big problem with inner classes is they're just too wordy, which they are. But their problems actually go much deeper than that. The rules for resolving names in inner classes are horribly complicated and Byzantine, because a name inside an inner class could refer to something in the lexical scope, or it could refer to something in the superclass hierarchy of the inner class. And it's very easy to make mistakes with this. It's complicated to specify. These complications, ripple through the tool chain, that they get in the way of other language features. They get in the way of VM optimizations. It's a bad situation. So we wanted to do better than inner classes, and rather than just saying let's have a better syntax for them. And at the heart of this question is, how do we represent a Lambda expression not in the source code? Everybody knows, everybody has an opinion about what syntax you should use for expressing a Lambda expression in the source code. But the harder question is, what should it look like at runtime? What should it look like in the bytecode? And we need a clean story at the bytecode level, the language level, the VM level, the machine code level, and again, that's that's what this talk is about. And the runtime representation is really important. I mean, it's really tempting to say, we should design the language to stand on its own and then worry about the implementation. But we also want these things to run efficiently on the JVM. And if there's a mismatch between how things look at the language level and how they look at the VM level, you lose, right? So we want to not lose. OK, so one of the obvious questions is, here's a new expression I want to add to the language. First question you might ask, well, what is the type of that expression? Java is a statically typed language. Every expression has a type. So you should be able to answer, what is the type of a Lambda expression? If you look at other languages that had closures built in from the beginning, there's an obvious answer. It's a function type. It's a function from int to int. It's a function from string to long, et cetera. And in fact, many of the earlier proposals for Lambdas in Java included some notion of, let's add function types to the type system, which is an obvious idea. So why wouldn't we do that if that's the obvious idea? Well, so one of the problems is a lot of these proposals didn't go any deeper than the syntax. This is how I would write it, but they didn't talk about how it will be represented at the VM. And we need a good story for how these things are going to be represented at the VM. And this isn't easy because there are a number of mismatches here that would have to be navigated around. Java is almost entirely nominally typed, right? The type of, types are defined by their name: string, map, hash map. There's one exception is array types, and array types are actually the source of a lot of corner cases with things like array store exception and arrays are covariant but generics aren't, and all of that. So mixing nominal and structural types is not anything that any language has gotten right yet. That's not to say it's impossible. There's been a lot of research. There's been a lot of commercial attempts. But if no one's gotten it right yet, that's a warning sign that what you're doing has a good chance of going wrong. And similarly, the Java language type system and the Java VM type system are different. And so if you add something new and complicated to the language type system, you're increasing the gap between the language and VM type systems, and that seems risky too. So these are kind of like the warning lights that are going on when someone says, why don't we just add function types? I love the word just. I learned this trick from my kids, right? If you want something unreasonable, put the word just in front of it, and it makes it sound more reasonable. Why don't you just give me a bigger allowance? You have more money, you could do it. Right? So you can make almost any bad idea sound like a good idea by putting why not just in front of it. It's a great trick. So why not just add function types? Well, all right, let's think about that. There's a lot of questions we would have to answer if we chose to add function types to the type system. How would we represent functions in a method signature, in a field signature? Could we say class foo extends function? Well, if it's a type, you have to answer the question about, can I put that type in every place a type use is allowed by the language? Can I cast to a function type? Can I say instance of a function type? Is it a subtype of object? Lots of questions. And we need a way to write something like, if I have a method and its argument is going to be a function from string to int, I need a way to write that in the bytecode. Currently, in the bytecode, method signatures are totally nominal. I have either a one-letter designator for int, long, double, boolean, et cetera, or I have a way of saying the name of this type, which is written in this horrible syntax of the capital letter L, the fully qualified, a Java/lang/object semicolon as a terminator. So I would need some new way of writing that, and the VM would need to know how to deal with that. Similarly, when I want to invoke a method, I have to name the whole signature of the method that I'm going to invoke. So I have to have a way of writing that invocation at the use site. I have to have a way of creating these things. Right now, objects are created with the new bytecode, so will we have to extend the semantics of the new bytecode to support new functions? Would there be some other way of doing it? And then there are the mismatches between the language type system and the VM type system, like wildcards, right? If I have a function from question super t to question extends u, well, the VM has no way to write that right now. So just add function types is a pretty tall order. So the closest tool we would have for representing something like function types in the bytecode without having to completely redesign the way signatures look in the VM is generics. So we could do the thing that other languages do, which is have some generic types, function 1, function 2, function 3, function 4. That means that all types are boxed. So a function from string to int is really a function from string to integer, and you'd better hope that your VM's going to do some good unboxing optimization in order to get you out of that pain. And similarly, generics are erased. So I couldn't overload a function that takes, a method that takes a function from, say, string to int against a method that takes a function from long to double, even though those types have no relationship with each other. And if people hate erasure in its current form, turning up the knob on erasure and say, let's have 6 times as much, well, that's going to be really popular, right? How many people here like that idea? Yeah. So function types are great. I love function types. Boxed, erased function types would suck. So let's not suck. This is an example of where we have a gap between the language and the VM representation, and these are always pain points, and you can kind of like push them under the rug, but they're going to come back to bite you. So teaching the VM about real function types would have been an enormous effort. We would have needed new kinds of type signatures, new bytecodes, new rules in the verifier to pass types around and verify that we weren't converting a pointer to an integer and things like that. You know, why not just add function types? Well, because it would have taken 10 years and it would have sucked. Okay, so instead, because we're lazy, we decided to do something much simpler. And we took a page from history and we said, all right, well, how do people write libraries in Java today that have callbacks or that use functions? And the way we do that is we model them with interfaces that have one method, runnable, callable, what have you. This is something we've been doing for 20 years. So rather than invent something new and complicated, let's just take something we've been doing for 20 years and we'll pull a good trick here. We'll give it a name. Giving things names makes them important, right? So those one-method interfaces you've been using in Java forever, like runnable and callable, they now have a name. They're called functional interfaces. How many people here knew you were programming with functional interfaces all your career? And this gives us an answer. To the question, what is the type of a Lambda expression? Well, it's a functional interface. If you have an interface like predicate here, which has one method, which is morally a function from T to Boolean, and you want to assign a Lambda expression to a predicate of, let's say, a predicate of person, it's going to look at the Lambda expression. It's going to compare the arity of the Lambda expression with the arity of the sole function in the interface. It's going to compare what it knows about the type information. It'll do some type inference. It'll do some type checking. And in this example, it says, yeah, I could convert this Lambda expression, p maps to p.getAge is greater than or equal to 18 to the interface predicate of person. So that's what you want. You assigned it to a predicate of person. I can do that. So this is kind of a simple story, which is we have this mechanism we've always used. The type of a Lambda expression is whatever functional interface you assigned it to. So this is one of a few examples here where there was a question that was obvious and wrong. The obvious answer was just add function types, and that turned out to be the wrong answer. And one of the questions that people ask the most frequently about big efforts like this is, why does it take so damn long? How many people here, I bet some of you have asked that question, right? Like, it's a simple thing. Lambda expressions have been around since, before my father was born. Why is it so hard to add this to Java, right? And the concept is straightforward, but figuring out the right way to integrate it into the language isn't straightforward, and there's a lot of obvious and wrong answers along the way. And if you just jump at the first answer, you're going to get it wrong. So something really cool happened here, and by ignoring the wrong answer and picking this weird answer, we get this form of compatibility that we never knew we wanted but now can't imagine living without, which is, if we had said we're going to add function types to Java, we would have immediately bifurcated the world of Java libraries, which is enormous, into old libraries and new libraries. And we would have spent the next 5 years retrofitting our old libraries to work with new libraries or to be new libraries. Now, there's just libraries, and all the old libraries that allowed you to program in this style, that had interfaces like predicate and function, of which there are many, just work with Lambda from day one. Okay, so sometimes the shiny new thing is not what you want. Sometimes the crusty old thing is actually a much better choice. So there's a world of libraries out there now that are ready for use with lambdas in Java from day one. Things like Apache Commons and Guava, and and a number of libraries in the JDK. By not introducing a new concept, we avoided the opportunity to have a multi-year incompatibility festival like we did with the generics. So sometimes doing the dumb thing is the smart thing to do. Okay, so let's look at another question that comes out of this. What should the bytecode representation of a lambda look like when the compiler comes across a lambda expression in the source code? What bytecode should it admit? So we've already said we have to convert a lambda expression into an instance of a functional interface. And for some lambdas, that's all we have to do. And for other lambdas, we have to also deal with the fact that we're capturing values from the lexical context, and we have to somehow bind them into the lambda. So there's another obvious choice, which is, well, translate it to inner classes. Make lambdas be syntactic sugar for inner classes. Most of the community assumed that this was really the only option. And we actually could have been done a lot faster if we decided to go down this route. I mean, we could have been done in like a day and a half if we went down this route. But there was a really good reason why we didn't go down this route. So we could say lambda is just an inner class, and we could have the compiler desugar a lambda expression into a class that looks like this, where for whatever captured variables you have a field and you have a constructor argument and you inject them into the into the constructor, and then the body of the single method of the functional interface maps to the body of the lambda, and everything's good. And then capturing a lambda is a really simple thing. It turns into a constructor invocation. So that would have been really easy and straightforward. So I'll show you what the bytecode for that looks like. It's also fairly straightforward. Like I said, the Java bytecode is stack-based. So these load instructions push things on a stack. So we're saying, take our list variable, push that on the stack, create a new foo$1, and then we're going to call we're going to push the captured argument on the stack. We're going to call the constructor for that new foo$1 that we've created, and then we're going to call the remove if method on the list that we pushed on the stack way up at the top. Okay, like I said, very straightforward. We could have done that, in a few days. But as I mentioned, we don't really like inner classes. And it's not just syntactically that we don't like them. We don't like their naming lookup rules. We don't like their performance characteristics. We don't like the fact that inner classes always capture the enclosing instance, whether it needs it or not, which can be an issue for garbage collection. We don't like the fact that there's one class per lambda expression. We don't like the attendant type profile solution that shows up as a result of that. We don't like the fact that there's always allocation, even when there doesn't need to be. We don't like the name lookup rules. And here's the kicker. We have this really strong commitment to compatibility. Whatever we do, we're committing to supporting for the next 20 years. So whatever bytecode the compiler happens to emit the day after Java 8 ships is the binary representation for a lambda for the rest of time. Well, we don't like inner classes as a binary representation, so why would we enshrine that for all times as our representation? We don't want to be stuck with that. And so this is another one of those choices that's obvious but wrong. So let's look at some alternatives. In Java 7, we added a mechanism called method handles. So a method handle is, in some sense, a VM-level closure. It's a reference to a method, and it can deal with bound arguments and things like that, just like a closure can. And you can store them in the constant pool of the class file. You can load them as constants. You can use reflection-like APIs to get a method handle for any method. And there's a nice API for building method handles out of other method handles of compose these two method handles, curry this argument onto this method handle, reorder, box, unbox, cast, etc. the arguments. So it's basically a Swiss Army knife for compiler writers, which is great. And it maps, not surprisingly, to a variant of the Lambda calculus. And so it's something that the VM is able to optimize very effectively, and that's all good. So why not just use method handles, right? Again, seems like an obvious idea at first. A lambda is a language level method object. A method handle is a VM level method object. What could be bad about this? So we could do that. We could say we're going to desugar a lambda expression to a method, and then wherever a lambda expression or a function type might appear in a method signature, we'll just use the type Java lang invoke method handle in that place. So here's kind of what the code would be transformed into. We have a lambda expression whose body is is the age of my parameter less than min age. So we desugar that to a method. So we create a static method there that has an extra argument where we can inject the captured minimum age value. And then we would say, get me a method handle for that method, and let me do this currying operation, insert arguments to insert the min age argument in, and then let me just pass that method handle to remove if. Done, right? We could have done that. But let's pull on that string and see where it leads. So if we did this, the signature of the remove if method on list would take a method handle. Well, we already talked about why using generics would stink as a representation for function types, because they're erased. Well, method handles are erased too. This means all methods that take one function as an argument would all have the same erasure. You couldn't overload methods that take different shaped lambdas. You couldn't overload a method that takes a string to an int against one that takes an int to an int. And erasure is bad enough when you try to overload a method that takes list of string and a method that takes list of shoe, and at least you see there's something in common. So when you get that error message and it says both of these methods have the same erasure, you kind of look at it and say, oh yeah, okay, I get it. But if you got that error message for this overload, you'd say, what are you talking about? These don't have the same erasure. So it would be leaking a implementation detail into the user visible programming model in ways that I'm sure would make programmers very happy, right? So, it gets worse, right? We would still need to encode the erase type information somewhere for the compiler to be able to use it to do type checking. And there was this lingering question surrounding method handles of, well, are they going to be as fast as the old style invoke bytecodes? Maybe yes, maybe not, but that's just a cloud of uncertainty hanging over this. But the big mistake that this approach makes, which is the same mistake as the other approach makes, is conflating the binary representation that we have to support for all time with how did we decide to implement it on Tuesday? Okay, so again, obvious answer, wrong answer. This is why this takes so long, right? That, for whatever answer we came to, we explored a lot of alternatives, implemented a lot of them, decided they sucked, and started over. So, what do we want? We want to have a binary interface for describing a lambda or a function type that's not tied to a particular pattern of bytecode that we want to generate for that lambda. Inner classes, they come with too much baggage. Method handle was too low level, it's erased. And unlike in some other languages, we consider it unacceptable to tell people, oh yeah, you have to recompile your code. We don't, in 20 years of Java, we've never said that, we're not going to say it. We care about binary and source compatibility way too much to be willing to, sorry, Jamie. I know Jamie's shaking his head in the back. But so this is a hard problem, right? This is a very heavily constrained problem. Well, what's the answer to all hard problems in computer science? More indirection. That's what we need, another level of indirection. So abstractly, what we'd like is for the compiler to emit not the bytecode that implements the lambda, but some kind of declarative description of, if you were going to make a lambda, here's the ingredients you would need, and go make it, right? And let the runtime use whatever means it has at its disposal to do that. Oh, but it has to be really fast. It has to be at least as fast as inner classes. Okay, well, that's harder. But we do have a tool that lets us do that, and it's actually quite cool. It's called invokedynamic, and this was the first bytecode added to the Java instruction set since Java 1. This was added in Java 7. And interestingly, it was a tool that was added for dynamic languages. And Java is a dynamic language, and it isn't. I have a lot more to say about that in my talk tomorrow. But we don't generally think about Java as being a dynamic language because it's very heavily statically typed. When I invoke a method, I know exactly what the types of the parameters I'm invoking are, and when that method gets linked by the JVM, they have to be an exact match. So we've already seen an example of one of the invoked bytecodes in earlier code. So in Java, from the beginning, there were 4 bytecodes for invocation: invoke static, invoke virtual, invoke interface, and invoke special. You can think of invoke special as the grab bag of everything that didn't fit in the others. Invoke static, that's obvious what that does. Invoke a static method. Invoke virtual invokes a virtual method on an object. Invoke interface invokes an interface method on an object, a virtual method. And then invoke special is like I said, the garbage pit for constructors and private methods and supercalls and anything that doesn't fit nicely into the others. What's common to all of them is the operand of the invoke bytecode has a enclosing class name, a method name, and a full-blown method signature that has to match exactly. And there's an example here at the bottom for those of you, who are actually close enough to the screen to read it. So invokedynamic is a 5th invocation bytecode. The observation is the old invocation bytecodes have fixed semantics. They're very much drawn from the Java language semantics, and not every language that runs on the JVM has exactly the same method invocation inherent semantics that Java does. So we need a way to allow languages to represent their invocation and inheritance logic in a way that's scrutable to the VM, where the language can help the VM make linkage decisions, and this is the important part, get out of the way. So you can implement any bizarre inheritance or linkage rules with reflection, but it's really slow. And we'd like it to be both flexible and not slow. So the idea is a language runtime encapsulates its linkage rules about when you invoke this method on this object with these types, here's the target that you should call. And not only that, it can also associate metadata with that linkage result of, and if none of these things changes, don't ask me again, just reuse the result, and then the language runtime can get out of the way. So it started out with a target profile of something like, your method call in Ruby, where you have no types. You have this add method that could take ints, could take floats, and the types aren't known at compile time, and they could change from call to call, but in reality, they usually don't. If you have a method, like this one in Ruby, where you're being called with 2 things you're going to add together, and I call it with 2 ints, there's a really high probability that the next time I call it, I'm going to call it with 2 ints again. And I'd like to be able to very quickly say, oh yeah, I've already made this linkage decision. I don't need to go through the slow linkage path. I can just verify, yep, int, all right, away we go. And so the win comes from moving logic from invocation time to linkage time. Linkage happens once, invocation happens every time you call a method. The more work that we can move from invocation time to linkage time, not only do we save all that linkage work, but there's a hidden dividend that comes from that, which is we get much better inlining. Because there's less work being done at invocation time, you're more likely to be able to inline through the invocation. Okay, and that's where performance comes from in basically every non-trivial runtime environment. Inlining is the dominant factor of what makes things go fast. So anything that gets in the way of inlining is suspect. Okay, so a little bit of a background on how invokedynamic works. The first time you stumble across an invokedynamic instruction in the bytecode, what the VM is going to do is going to say, all right, I need help linking this call site. Someone has asked me to call something. I have no idea where to go, but fortunately, at the call site, there's something called a bootstrap method, which is what I'm calling the language logic, which will help me link the call site. So the VM invokes the bootstrap method, and the bootstrap method returns an answer that the VM understands about, here's who to call, here's the conditions under which you have to ask me again. And if your linkage is completely static, that set of conditions is empty, and the VM is free to say, okay, I can inline through this for the rest of time. So after this linkage happens, as long as you don't violate whatever guard rules were passed back from the bootstrap, the VM can treat the site as fully linked and then inline through it in future invocations. All right? So it's a way of letting the language runtime participate in something that the VM is already doing, which is dynamic linkage, but not requiring that that happen every time you call the method. Okay, so the things that are present at an invoke dynamic call site are more complicated than a typical invocation. There's three things. There's the bootstrap method, or the language logic. That's called by the VM on first invocation. There's a static argument list, which is basically the argument list for the bootstrap. It's things that the compiler has identified about the call site that it knows are not going to change. And then there's the dynamic arguments, like the things that you're actually adding together. And even though the bootstrap doesn't see what the dynamic arguments are, because they're going to change from call to call, at least the bootstrap knows how many they are and what their types are going to be. And so you have a little bit of an idea of what you're being asked to do. I know this is complicated. I'll connect it back to reality in a minute. So the key observation here is, well, this was supposed to be a tool for dynamic languages. Why is the Java compiler so interested in using this tool? Because all the types involved are static. Well, what's dynamic here is not the types. What's dynamic here is the code generation strategy. I just outlined 3 different code strategies for, well, I outlined 2. I can name others. I could generate inner classes. That's one code generation strategy. I could use method handles. I could use other strategies like dynamic proxies if I really hated myself. It might be that my VM has some low-level alchemy for constructing objects out of raw bits, and I might choose to construct my Lambda objects that way. And that's dynamic because that's happening at runtime. I don't have to pick that strategy at compile time. All I have to say is, I want a Lambda with these characteristics, and if the runtime can come up with a faster way to make it, I'd like to enable that to happen. So using invokedynamic turns this choice, which had been something that you had to do at static compilation time, into a runtime implementation detail. So we're able to separate the choice of how we generate the bytecode from how we describe what needs to be done. And so what we do is we use invokedynamic to embed basically a recipe for constructing the Lambda, which includes a method handle to the method that implements the body of the Lambda. So the compiler desugars the method body the Lambda body into a method, and we just pass a method handle to that method. What functional interface are we converting to? Predicate, function, runnable, what have you. Other metadata that the compiler might have statically identified about the call site, like, is this Lambda supposed to be serializable? Yes. And any values that might be captured from the lexical scope. And those are dynamic properties. Those are going to change from invocation to invocation. So we call this site the Lambda factory, because the idea is when you want a Lambda, you invoke this invokedynamic method, and it hands you back the Lambda. So that's the Lambda factory. You invoke it using invokedynamic. It returns an instance of the desired functional interface, a function, a runnable, a predicate. And then the next time you hit that point in your code again, it's already linked. So we bypass the slow linkage path, and in fact, we may bypass the invocation path as well. I'll talk about that in a minute. Okay, so how does this work? First thing the compiler does is desugar the Lambda to a method. This is compiler 101. The signature is going to match the functional interface signature, plus if there are captured arguments, those will get prepended to the argument list. So really simple Lambdas desugar just to static methods. Lambdas that capture this get desugared to instance methods. So we do the simplest thing that we can based on what we can discover statically analyzing the body of the Lambda. And then we generate an invokedynamic site, which when called returns the Lambda. Like I said, we call that the Lambda factory. So here's kind of what it looks like. We start out with a Lambda in the bytecode. We translate that into an invokedynamic whose bootstrap is the Java language runtime for make me a Lambda. We call that the Lambda metafactory because it does the linking for the Lambda factory site. The static arguments are, what functional interface am I converting to? What body implements this? And are there any dynamic arguments? And then what gets returned is actually an instance of predicate. So I just pass that to remove if, and I'm done. In the simple case where I'm not capturing any arguments, some really nice optimizations are possible. Okay, so what could happen here? So the metafactory could say, all right, I need a Lambda which implements the interface predicate, and when you call the test method on predicate, it calls this method over there. So it could just spin bytecode to implement something that looks a lot like an inner class. And that's in fact what the current implementation does, but that's just now a pure implementation detail. And then we link the call site, the factory call site, to the constructor of that thing. This is actually a pretty reasonable initial strategy, but there's other strategies we could use too. We could spin one wrapper class per functional interface, one wrapper for callable, one wrapper for runnable, one for comparator, one for predicate, and have the constructor for that thing just take a method handle that implements the behavior. We've also implemented that. We could also use dynamic proxies or anything else. And what we've done is we've bought ourselves an opportunity to procrastinate. We've said we're going to defer the code generation strategy to runtime, which makes the code generation strategy a pure runtime implementation detail. We can change it dynamically. We settle on a binary protocol now, which is the API for this so-called metafactory, but we don't have to bind to a choice of code generation strategy until you actually run your program. So this is a part of a long history of moving work from static compilation time to dynamic compilation time, right? And this is one of the counterintuitive things about why Java is faster than C++, which is the quality of your code is dependent on the quality of the decisions you can make. You can make better decisions when you have more information. At runtime, you have more information. You have type information. You have profiling information. You have how often has this back branch been taken versus non-taken, and you can use that information to generate better code. So Java is all about statically typed at compile time, but all the implementation decisions, let's move those to runtime where we can make better optimization choices. So this is, in some sense, consistent with the way we've been doing things in Java for hundreds of years. And it gives us an opportunity to change our code generation strategy, from one VM version to another, across Oracle's to IBM's VM, or even like on Tuesdays we could have a special strategy and no one would care. Well, they might care, but it wouldn't be breaking the rules. Okay, so invokedynamic was cool for procrastination. It's also a tool for lazy initialization. This is where it starts to get really cool. So if you've been sleeping, wake up. The most common form of Lambda are what we call stateless lambdas. Lambdas that don't capture anything from the lexical scope. X arrow x plus 1, right? This is a pure function. We call this a stateless lambda. It only refers to its arguments. And it's not the only case, but it's a very common case. Let's call it 50% or more. Now, if you write code with inner classes yourself, you've probably done the trick of saying private static final comparator C equals new comparator blah, because you've manually hoisted it to a static context, because you've observed that you only ever need one instance of this thing, right? How many people here have done that trick? Okay, the compiler does this trick now for you routinely. Okay, you never have to do this trick again because the VM is going to look at this lambda, say, this is non-capturing, it's stateless, I only ever need one of these. So at linkage time, I'll allocate one, and then I will optimize the invocation of the Lambda factory, which sounds expensive, into a constant load. So I don't have to create new objects each time I want a new one of these. I don't have to call anything. All of that expensive linkage path, which involved like spinning bytecodes and loading classes, sounds incredibly expensive, gets optimized to 0. Absolutely no cost. All right? So invokedynamic lets us basically use a call site as a lazily initialized cache. The initialization cost happens only the first time you invoke it. There's no heap overhead, there's no extra field the way you would if you did it manually. There's no static initializer. And then once you call this thing once, you get this lazy initialization and caching for free, and this happens for all stateless lambdas. So that's really cool, right? That's a huge, huge payoff for having picked this, what some people might describe as an incredibly complicated implementation strategy. But wait, there's more. So like I said, the answer to all hard problems in computer science is an extra level of indirection, and this invokedynamic gives us an extra level of indirection for deferring the choice of strategy without paying for the choice of that strategy on every call. So the metafactory gets invoked once per call site. In the non-capturing case, subsequent captures are totally free. The VM optimizes that to a constant load. In the capturing case, what we do is we link the factory call site to the constructor of a generated class, which is basically exactly as expensive as an inner class was. And thereafter, after linkage, the capture cost is the same or sometimes cheaper than an inner class. So I keep saying faster, so you're probably thinking, do you have numbers, right? Because it's easy to say something's faster. But so I have a few performance numbers here. So actually, is this a 1-hour talk slot or a 50-minute slot? Does anybody happen to know? I could talk faster if it were getting on. Okay, we're on to 11:15. Okay, great. So I could talk faster, believe me. So if we break down the cost of a translation scheme, there are actually 3 layers of cost that we care about: link time cost, capture time cost, and invocation time cost. Link time cost is the one-time cost of the first time you evaluate one of these lambdas. Inner classes have a link time cost too, right? The first time you say, new foo, inner class, blah, 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 it's going to go out to the file system, get the bytes for foo$1, do class loading on it. That's a link time cost. Capture cost is the cost every time through that code that says, give me this lambda expression. And then invocation cost is the cost of actually applying the lambda, invoking the lambda. And these are completely separate costs, and we can measure them separately. So for inner classes, the costs correspond roughly to linkage cost is loading a class off the file system. Capture cost is invoking a constructor. And invocation cost is generally an invoke interface or an invoke virtual invocation instruction. So I had my performance team run some measurements. They ran this on, I think this was an 80-way Nehalem box. And this, I have 2 charts. They're measured a little bit differently. So the first one is linkage cost. And this is time in milliseconds for loading 32,000 distinct either lambdas or inner classes, using a RAM disk to not be biased by the fact that maybe going out and getting bytecodes off disks was slow. We actually have like 4 different measurements because we wanted to separate capturing lambdas from non-capturing lambdas, and we also wanted to separate measurement using different VM settings. Tiered compilation could really mess with performance settings, so we generally report numbers with both. The important thing to notice is the linkage cost for lambda is faster, sometimes significantly faster across the board, right? So when we started this, a lot of the naysayers were saying, just use inner classes. You're never going to do better than inner classes. It can't possibly be faster than inner classes. Well, so much for that. So link time faster than inner classes. Let's look at another measure, which is capture cost, right? This is capturing a lambda, what we call evaluating but not invoking a lambda expression. Again, 80-way box. The summary here is, in the worst case, a capturing lambda, we got performance that was basically equal to that of inner classes. But the best case numbers were much, much better. The really interesting one is that second line, where we have a non-capturing lambda, where this is these numbers are how many operations can we get per microsecond. What we see here is, if we're running single-threaded, we're able to get 230 operations per microsecond, basically 4 nanoseconds per capture, which is basically the cost of moving 1 or 2 fields from memory to memory. If we compare the single-threaded to the let's let 80 threads run on this 80-way box, what we see is with inner classes, we end up maxing out at about 5 threads. And that's because inner classes are doing allocation, and eventually you're going to bottleneck on that. With the non-capturing case, we see scalability of almost 70x, which reflects the fact that these aren't real cores. I mean, these are like, so they're 2 threads per core. Basically, you're able to run at full memory bandwidth. All right. So, in the worst case, like a capturing lambda is exactly the same as an inner class. A non-capturing lambda in the single-threaded case is about 50% faster, and in the saturated case is about 12 times faster. So significant improvement over inter-class performance. And this is with the dumb strategy, All right? We picked like the dumb strategy that we shipped with, and we're still better than the obvious why not just do interclasses strategy. There's a deep pipeline of improvements we can make to make this faster, but like I said, we're going out the door with a dumb strategy that's already faster across the board than the obvious strategy or the old way. Okay, so a couple more things, and then I'll wrap up. So one of the cool things that we did here is we tried to put as much of the tooling outside of the Java language space and into the JVM space as we could. So the mechanism for creating a Lambda from a factory, from a description, is part of the language runtime. We hope that other languages will just use that to build their closures as well, and then they will get the benefit of future performance improvements, just like Java will. So what we've done, is a lot of the machinery for doing this, all the bytecode spinning and all of that, is something that any other compiler can just pick up tomorrow and start using and benefit from the improvements. Similarly, the Java APIs are full of functional interfaces, not just the old ones like Runnable and Comparator, but the new APIs like the Stream API are full of functional interfaces. Since other languages will probably want to call these Java libraries, and they may want to call it with things that look like closures, they may want to use the same mechanism for converting closures to Java objects. So we tried very hard to share the benefit with other languages that run on the JVM. I could hand wave a little bit about how this will get better in the future. We already know a number of things that we can do to make this a lot faster. So because we've embedded not bytecode for how to make the Lambda, but an actual declarative recipe for what the Lambda is, this is something that could be intrinsified. The VM could recognize it. It could say, oh, I know what that invokedynamic means. It means convert this behavior to this Lambda interface. I know that that's a pure operation, so I can do code motion on that. I know that Lambda capture is essentially a boxing operation. I know Lambda invocation is essentially an unboxing operation. I have existing optimizations for box-on-box elimination. Maybe I could move the capture site close to the invocation site and have the box, the boxing go away. This is like totally tractable. We haven't implemented this yet, but it's totally tractable. We have every reason to believe that what is fast now will be faster in the future. Okay, so let me end on a down note. Some of you may know that I never miss an opportunity to take a swipe at serialization. This is the worst language feature ever to make it into a mainstream language that ever got any popularity. And it's the gift that keeps on giving. Every language feature that has ever been invented and ever will be invented has some horrible, non-trivial interaction with serialization. And Lambda was no exception. And I would say we probably spent 20 to 30% of our effort, probably closer to 20, but it felt like 200, on how are we going to deal with serialization. We tried really hard to hide our heads in the sand and say, well, the answer is just don't do it, but that's not really an acceptable answer. And this little snippet of code, if you think about what's an ordinary user going to think about this code, gives you the answer, right? If you say interface foo extends serializable, it's clearly one of these functional interfaces. I'm going to convert a Lambda that captures nothing to that serializable thing. Of course they expect it to be serializable, and if it isn't, they're going to hate us, right? And of course, since we want to be liked, that's the most important thing that we optimized for. Now, because we have a dynamic code generation strategy, we can't just serialize the Lambda object because the class for it won't exist at deserialization time. Oops, what do we do? Well, if we have a dynamic code generation strategy, we need a dynamic serialization strategy. And of course, we need to do it without exposing any new security holes, because serialization is the gift that keeps on giving. So just as our class file representation for Lambda was a recipe, our serialized form has to reconstruct that recipe. So fortunately, serialization provides tools for this. You have read resolve, write replace, where you can intercept the serialization and say, don't serialize the Lambda class. Let me reconstitute the recipe, and I will serialize that recipe to some holder, which we call serialized Lambda, and we'll serialize that. And that means that When we convert a lambda to a lambda object, we have to have a different path for serialized objects because we don't want all the cost of serialization to be borne by all lambdas. And then at deserialization time, we reconstitute from the recipe, and we use this like really clever Aikido strategy where to avoid a number of the security risks, we basically hand the lambda back to the code, to the class that it claims it was created by, and we say, do you recognize this as one of your children? And if so, I don't care how you do it, reconstitute it for me. And so the compiler generates extra code in the class file for reconstituting serialized lambdas. It's pretty cool, but it was really painful. So okay, I just had to share that. So you have to vent, otherwise these things eat you, right? All right, wrapping up. What I hope you'll take away from this talk is that the evolutionary path of adding a big new feature to a language that people actually use is full of obvious but wrong ideas. Your first idea is going to be wrong. Your second idea is going to be wrong. Just accept that, plan for it, and eventually some good ideas will occur to you, and as they did. But you never know what direction they're going to come from, so you have to give yourself some time to do that. We used invokedynamic here in the capture of lambda expressions, not because we had dynamic typing, but because it gave us the flexibility and performance to defer an important decision to runtime, and lets us change that if we come up with a better way of generating the bytecodes. And even using what I would describe as the dumbest possible, it's not the dumbest possible, the dumbest reasonable translation strategy, it's still no worse than, and in many cases better than, inner classes, which were the obvious alternative. So it is possible to get flexibility and performance. You just have to work at it. And with that, if we have any time left over, I'm happy to take questions. Okay, we have a microphone we can pass around. This gentleman has a question here.
Regarding the performance difference at linkage, do you have an explanation for why lambdas are faster than inner classes?
So the inner classes have more junk in them, and they take I suspect that they go through a somewhat different class loading path than what we're able to do when we've just spun the bytecode and are able to hand it to the VM. I actually don't know all the details of why. In the real world, you will see even more of a difference because it's the difference between going from memory to class loader versus disk to class loader. But the measurements that we showed erased that difference because we didn't want to be accused of biasing the measurements. It goes through a class loading process. It goes through unsafe.define anonymous class, which actually is part of the difference that because the class doesn't have a name, it doesn't have to get loaded into the system dictionary, which means it doesn't need to take a lock. So that's probably where most of the difference comes from. Another question over there.
There's code as data. How long before we get hygienic macros?
Probably a long time. Maybe you should rephrase that as, now that you have code as data, why not just add hygienic macros? It's a great trick. Works all the time. Do we have more questions? All right. If not, thank you very much.